In this video, we're going to go over significant figures. So one of the things that I recommend that you do is you take a look online at this stoichiometry tutorial, significant figures. The link to this significant figures tutorial can be found on Blackboard, and it's in the folder for Chapter 1 under Resources. So take a look at this because all of the rules that we're going to go over are already on here, so I'm not going to rewrite them. So like when I say Rule 1 and I talk about non-zero digits, that's all on here already. So I'm just going to be reiterating from this. And this also will take you through a lot of the other rules, like for how you do multiplication, division, and addition and subtraction. So I would recommend that you start here, and either you can print this out, you can have this open on your computer and just kind of follow along with the video. So the first thing we're going to do with significant figures is we're going to learn how to count significant figures. So this is going to pertain to the rules that I just showed you. So my recommendation is to either print out or have open that tutorial on significant figures and follow along with the rules. So the first rule, rule number 1, says that non-zero digits are always significant. So for example, if you have a number like 1.234, the number of significant figures in this number is going to be 4. Those are all non-zero numbers, so they all count. And for example, 79.1, that would be 3. And then if you have something like 1.23 times 10 to the 26th, this is going to be 3. Now, with scientific notation, and we're going to be using scientific notation a lot, we only care about this part of the scientific notation. This is just setting its position in terms of how many zeros you have either after or before that number. So rule 2 says that zeros between non-zero digits are always significant. So for example, if we were to have 100.2, the number of significant figures here, these two zeros come between the 1 and the 2. So all of these numbers are going to be significant. We're going to have 4 significant figures. If we have 670.03, even though there's a decimal place there, because they're in between two non-zero numbers, those are going to count. So this one's going to be 5. And if we were to have 1.203 times 10 to the 5th, again, we don't count the times 10 to the 5th, we just count these this part over here, so this would be 4. Okay, so let's look at rule number 3. So rule number 3 says leading zeros before the first non-zero digit, are not significant. So generally, this tends to be in circumstances where you have something that looks like this, 0.00471. These digits up here do not count. What these are doing is they're just setting where this is in terms of whether it's a tenth, a hundredth, or a thousandth. Those are not significant because they're not measured values. They're just setting where those measured values are in decimal space. So this one would only get 3, and these don't count. Now, a really good way to approach this is to write the number in scientific notation. So if we convert to scientific notation, we would write 4.71 times 10 to the minus 3. And the way that I did that was I just moved the decimal place over 3 times. So I write times 10 to the minus 3. And it becomes much clearer that there are only 3 significant figures, because those zeros that are here get wrapped up into the times 10 to the minus 3. So rule number 4 says trailing zeros after a decimal point are always significant. So let me show you what I'm talking about with number 4. So for example, if we have 12.30, this 0 counts, because what we're basically saying here is this is 12.3, and then we have this 0 here. Well, this is saying that this instrument could have read off a 1, 2, 3, 4, 5, or 6 here. It just didn't, because it read 0. So this actually counts. In essence, this is often what we refer to as paying for extra significant figures, meaning your balance could read out a value here. It just, in this case, it just decided that that value was a 0. So this counts. So the number of significant figures here would be 4. So extra zeros tell you that you could have a value there, it's just it isn't. Now again, let's look at this with scientific notation. So let's say that we were to have 0.002010. If we were to convert this, so we would count this as 4 significant figures. Now, let me show you why when we convert to scientific notation, that helps. This would be 2.010 times 10 to the minus 3. And so now you can see that all of those digits are significant according to rule number 4. And you see that these do not count. So these ones don't count because they're going into the times 10 to the minus 3, but this one does count because it comes after the decimal place. So this would be 4 significant figures. So let's look at rule number 5. So trailing zeros before the decimal point are ambiguous. To avoid ambiguity, use scientific notation to indicate the number of significant figures. So let's look at the example of 1200. Now, at Fordham University, we are going to say that this one has only 2 significant figures, and that's because we don't know if these count or not. Meaning, if there are zeros that come before the decimal place, we're not sure if these count. That's what it means by being ambiguous. So a way to not be ambiguous would be to write this in scientific notation and then include a 0 if you needed to. So for example, if you were to write this in scientific notation, we could specify 1.2 times 10 to the third, in which case it would be 2. Or if we wanted to, if you want 3 sig figs, you could write this in scientific notation but explicitly include a 0 after that, in which case this would become 3. This is an explicit added 0. So when it's like this, when it's written as 1200, 00, and the zeros, and there's no decimal point, nothing to indicate whether they're significant or not, then we're just going to assume that they're not. So that's what we do here. Now there's one other thing that you can do, and I'm just going to erase to get a little bit of room here. Another way that you could indicate, let's say that you wanted to indicate that those, that the 1200, that those zeros were significant. Well, what you could do is you could add an explicit decimal point and if you add an explicit decimal point, then they become significant. So then it goes from 2 significant figures to 4 significant figures. But my recommendation is not to do this. My recommendation is to use scientific notation, and then there's no possibility for ambiguity. If you write it in scientific notation with the correct number of significant figures, that's going to get you the best result. So let's look at the rules for how we start to use these in functions. So there are a couple of things. So we can have multiplication and division. That's the first one. So the rule for multiplication and division is that the number with the least number of sig figs determines the sig figs in the answer. So for example, if we were to take 1.74 times 4.3 and then we divide that by 3.42, now, and we divide that by 3.42, we need to figure out, well, how many significant figures are we going to have? So what you always do, no matter what, is you always plug this into your calculator exactly as it is and get a number. So if you were to plug this into your calculator, you would get 2.187719 is what you would get out of your, and it goes on, was what you'd get out of your calculator. But now we have to decide, well, how many significant figures are there in this answer? So according to the rule, we have to determine which of these numbers that go into it, the 1.74, the 4.3, or the 3.42, has the least number of significant figures. So this guy's got 3, this guy's got 2, this guy's got 3. So the one that's going to control it is the 4.3, which has only 2. So the way that you can denote how many the correct number of significant figures is by putting a line underneath at the correct number of significant figures. So we decide that the answer is supposed to have 2 significant figures based on the 2 significant figures of the 4.3, and then you can denote that by putting a line underneath. So we are perfectly happy with you when you do significant figures, just writing a number with a couple of extra digits and then putting the line underneath. This will oftentimes show the professor that you did everything correctly. We don't want you to round. So whenever you're doing these things, the most important thing is round at the very end. So you should never, like in a multi-step process, you should never round until you get to the very end. So you should be taking your numbers with extra significant figures every single time and then rounding at the very end. So you can use this line underneath to allow you to carry numbers through your calculations with the proper number of significant figures so you don't get confused. So you might be wondering, how do I report this on the exam? And you have two options. A perfectly good option on the exam would be to write 2.187 or something like that and put the line under the 1. That's perfectly fine for us. And then the 87 just shows us that you didn't round and that you have roughly the right number. So if you keep an extra couple of extra, you don't have to unload your calculators at us. We don't want like 7 digits like this. But like 1 or 2 extra afterwards is perfectly fine, and that just shows us that you got the right number. And then this line indicates that you have 2. Or you can round. So option number 2 is to round. Now, if you round, you have to be a little careful. So you could round this to 2.2 and write it like that. And this number has 2 significant figures, so that's fine. If you round, the rounding rules are as follows. If it's greater than or equal to 5, it rounds up. If it's less than 5, it rounds down. Okay, so that's what you would do with rounding. So in this case, it was 2.18, so I rounded it up to 2.2. So with addition and subtraction, the rule basically is the sig figs of the answer is determined by the least precise decimal. And I know that's a little complicated. So for example, let's say that you wanted to add 12.346 plus 102.34. So what do I mean by the least precise decimal? So we don't care about the overall number of significant figures. We care about the one that's to the least precise decimal point. So if you look, this goes out to the 3rd decimal point. This only goes out to the 2nd decimal point. So this is the one that's going to control. And let me actually show you a simple trick for this. If you take the 102.34 and you put it above the 12.346, just like this, like you normally would add 2 numbers together, well, you plug it in and you plug it into your calculator, you're going to get a number. So you're going to get 686 you're going to get 114.686. Now, what you're going to do is you're going to drop a line at the least precise decimal point. So if you look, the 4, there's no significant digits past that 4. So I'm going to drop a line here, and I'm going to say everything to the left is significant. Everything to the right is not significant, because this one is controlling, that 4 is controlling the overall accuracy to the decimal points. So the way that you could report this is your first option would be 114.686 with a line underneath, or 114.69 would be valid ways of reporting that. Now, here's another possibility for when you have to add something. Let's say that you wanted to add 2.7 times 10 to the minus 3rd plus 140.003. Now, this is an interesting case because now you have something that's in scientific notation and something that's not. So what I recommend that you do for this is you take this out of scientific notation. So you put your 140.003, and then you would add to this 0.0027, and then again, now you can easily find your least precise digit, decimal place, which is the 3 in the 140.003, and then when you plug this into your calculator and you add it up, you're going to get 140.0057. And so you're going to take these as being the significant figures. So you would report this as 140.0057 with a line under the 5, or as 140.006. Either one of those would be fine. We're going to look at So the next one is we're going to look at one more, and this is exponents. So let's say that you have 2.00, so 3 significant figures, and you want to take this to the second power. Now the second power, this is no significant figures, meaning when you take something to a power, that power is not a measured value, so it has no significant figures. We don't count the squared. Really, the way that you can think about this is really like saying this is 2.00 times 2.00. So this is going to equal 4.00. So whatever the number of significant figures is in the number, is going to equal the number of significant figures in the answer. So in the second to last part of this video, we're going to put it all together. So we're going to look at how we combine adding, subtracting, multiplying, and dividing. And the rule is that you have to use order of operations. And that is PEMDAS. So the P stands for parentheses, exponents, this is multiplication and division, and this is addition and subtraction. And so because of the associative rule and because of the basic rules of math, multiplication and division, there is no preferred order, meaning you can do multiplication and division, it will always be the one with the smallest number of significant figures that controls, regardless of the order. So multiplication doesn't have to come before division or vice versa. They can be done all together, and you're just going to use the same rule. And the same goes for addition and subtraction. They can be done all together. It just, you need to use the same rule for adding and subtracting, which is to drop your line at the least significant digit. So let's look at how we can combine some of these things. So let's do 32.5 plus 17.02 in parentheses. Then we're going to multiply this by 19.2, and we're going to divide by 14.06. Okay, so now let's follow our rules. So our order of operations is first parentheses. So step 1 is going to be to take care of the parentheses. So let's add up our 32.5 and our 17.02. So we use our rule. We're going to drop the line at the least significant decimal place, which is the 5. And so we get, from this, we get 49.52. And I'm going to write my little line under the 5, and I'm going to keep all of my digits, okay? So because we have another step, I'm not going to round yet. I'm going to keep all my digits. This is really important. And you don't have to keep all of the digits, but you have to keep at least 1 or 2 extra. So you'll notice here that I have 1 extra one, and I'm keeping it. So I'm going to use that in my second step to calculate. And that's because if you round early, you're not going to get the same number that we're going to get. So you don't want to round until the very, very, very end. So I take this number and I go into step 2. So then in step 2 for this one, we have a multiplication and division. So I put my 49.52, I multiply that by 19.2, and I divide it by 14.06. And when you plug this into your calculator, you should get 67.6233, and so on and so forth. Now, if you're not getting this, it probably means that you rounded at some point. So to determine the number of significant figures in the final answer, we have to look at the number of sig figs in each one. And you'll notice that I make a little mistake. The 49.52 should have actually only had 3 sig figs because there's the bar under the 5. So in the end, we can report either 67.62 with a bar underneath the 6 because there should only be 3 significant figures, or we can report 67.6 with rounding. So the last thing we're going to talk about is an exception to the significant figure rules. And there really is only one. And this is a value that is, how would you say? These are values that are exact values. So there are a couple of examples of this. One would be, for example, 2.54 centimeters equals 1 inch. This 2.54 centimeters equals 1 inch. Neither of these are neither of these values are measured. This is an exact value. By definition, there are 2.54 centimeters in 1 inch. So the reason why we use significant figures is because they are coming from experiments where we have measurements, and those measurements can have inaccuracy. Now, with a exact value like 2.54 centimeters equals 1 inch, there is no inaccuracy here. It is exactly that. It has an infinite number of significant figures. So the way to think of this is that these have infinite numbers of sig figs. Let's say that we have 1.574 times 10 to the minus 4 centimeters. And we wanted to convert this to inches. Well, what I would do is I would take my 2.54 centimeters for every 1 inch. Now, in this case, you might be tempted to either use 3 significant figures or just 1 significant figure based on this unit conversion, but you won't. Your answer here, you can calculate it, whatever it is. I don't know what the actual answer is, but the correct number of sig figs in the answer should be controlled by this number, which is measured. This is measured. This is exact. So this should have 4 sig figs in the answer. Another example of this is where you have something like a dozen. So you have 12 eggs in 1 dozen. Again, the 12 is not a measured value. We've defined that the dozen is equal to 12 eggs. So anywhere where there's a definition of one thing being equal to another thing that's not measured, then you don't include these in the number of significant figure calculations. You just use whatever the number of significant figures is in the measured value.